1/2 of f of x. And as long as that idea makes sense to you, then you'll never get confused about what is m sub x or m sub y, or is f a function of x or is f a function of y. You just always want to encourage you that to draw at least one of these rectangles to remind you what should be the sensible formula for the case that you're given. All right. Well, what about the moment about the y-axis? That's actually a little bit easier because remember, again, the center of each rectangle is located on that midpoint x sub I star. So I take the area to the x coordinate of the centroid. All right. And so the x coordinate is x sub I star. The area is the delta x times the function value at x sub I star. And then we let the number of rectangles go to infinity, we wind up with this integral here. So we've got this, in a sense, it's x is the weight. It's a weighting on f of x. And of course, the area is just the same area that we calculated in calculus 1. All right, so again, we take the sum of the moments. In this case, we use instead of a discrete sum, we have the integral that performs the sum over the entire region. And then divide it by the area. And the same thing in order to get the y coordinate. All right, so let's do an example here. I've got this upside down parabola. I want to find the centroid, or the center of mass, because this is the face of a lamina. And the region that we're interested in is bounded above by the curve and below by the x-axis. So we've got these formulas. We can go ahead and just make note. And anytime you have a lamina with a constant density and a constant thickness, then any line of symmetry has to pass through the center of mass. And again, that should go to this idea of balance, right? If you have a line of symmetry, the area on one side is the same as the area on the other. And so that line of symmetry should pass through the centroid, or center of mass. So here, this region is symmetric with respect to the y-axis, or the line x equals 0. And so I know that the x coordinate is 0. So that's an important idea. It can save you a lot of work when you recognize the symmetry. So let's just find then the y coordinate. In order to find the y coordinate, I need to know the moment about the x-axis. So I'm just taking 1/2, and then I'll take the function squared. I'm going to integrate that from -2 to 2. And I'm going to take advantage of the fact that this is an even function. All of the exponents it's a polynomial. All of the exponents are even. Even the 16, you think of 16 as 16 times x to the power of 0. 0 is an even number. And so instead of going from -2 to 2, I can make my bounds go from 0 to 2. And then I've got to multiply it by 2. And that's why I no longer have the 1/2, because I know that it's going to be twice the integral from 0 to 2. So then evaluating that's just using the power rule and doing the arithmetic carefully. And then I'll have to divide that by the area, which is essentially the total mass. And so again, I've got an even function, so I'll go ahead and take advantage of that symmetry and evaluate that integral. And then carefully, I'll just take the m sub x and divide it by a, and that will give me the y coordinate, which is 8/5. What's that? 1.6. So that point right there is our centroid. So let's go back to what we started with here, this cubic polynomial. And let's work out the centroid for this one. Now I don't have any symmetry, so I have to calculate both moment about y-axis and the moment about the x-axis. And I'll just use the formula to do that. I won't spend too much time talking about the details unless somebody has a question. And we'll go through that again. When you have polynomials, really, you just have to be careful with the algebra and use the power rule and make sure you get the evaluation correct there. And so then I can just take the moment about the y-axis, divide it by the area. That gives me the x-coordinate. And the moment about the x-axis divided by the area gives me the y-coordinate. So, as a memory aid, you can just say that, oh, it's always the opposite axes that you take the moment about. If I want the x-coordinate, you're taking the moment about the y-axis. If you're finding the y-coordinate, you're taking the moment about the x-axis. All right. So what if I have a x written as a function of y? And again, this is where things can get confusing if all you're doing is trying to memorize formulas. And so you could just take those same formulas and replace it. And I'm a little disappointed that I don't have drawn here. Because what I would encourage you to do, what I do in these cases, I say, oh, okay, I have x as a function of y. If I were trying to calculate the area, what I would be doing is I would be drawing a rectangle which is thin and its base is on the y-axis. And so once I've got that rectangle and I'm trying to think about, okay, what would be the moment about the y-axis? Well, let me just think about the moment of this one rectangle. It would be, well, the area of the rectangle, so it'd be delta y times the x coordinate. Well, x is my f of y. And then I would multiply that times the distance from the center of the rectangle to the y-axis, which would be half of f of y. So I know that this is going to have a half of f of y times delta y. And so when it becomes an integral, it's going to be the half f of y squared dy. And then the moment about the x-axis then, again, I'm just looking at this rectangle. I would say, well, it's going to be the y-coordinate of the center of the rectangle. And I'm going to take that y-coordinate and multiply it times the area, which would be the f of y, the x value there, x is f of y, times delta y. So I would really like to encourage you to always think of these in terms of having a reference rectangle that you can use to help you remember how these formulas come about, just to avoid the confusion. So in this case, then, I'm not going to go through all of the details. We'll skip this for now. And now let's assume that I have two curves. I have a top and a bottom. And we're referring to the top as F and the bottom as G as we derive this. And so, but you really should always think in terms of top and bottom. And so if I follow the same method, I'm saying I'm going to try to cover that region with rectangles, and I'm going to find the center of mass of each rectangle and then use that center of mass to get an approximate value for the moment about the x-axis or about the y-axis. If I bear that in mind, then I'll be able to remember these formulas, or at least derive them again. So the area again would be the height of the rectangle. That's the distance from the top curve down to the bottom curve. And so that's top minus bottom. All right. So we're calling the top F, we're calling the bottom G, but we really should be not memorizing F and G, but we should be thinking top minus bottom. That's the height of the rectangle, and delta X is the width. So that gives me my area. And then what about the distance then to the, well, what is the centroid of this rectangle? Well, the X coordinate is the X sub I star, just as before. It's the midpoint of that subinterval. And what's the Y coordinate? Well, I'm sorry, yeah, the Y coordinate of the centroid. Well, it's going to be halfway up the rectangle, but the rectangle is already a distance away from the x-axis. But we know that distance. That distance is the G value. And then we're going to add it. Then what's the halfway up? Well, halfway up would be half of the difference between the top curve and the bottom. So it would be the bottom plus half of the difference between the top minus the bottom. Now we can do some algebra to simplify that. We're going to get some like terms because we'll have a 1g of x minus a half g of x. That's half g of x. And then this actually makes sense. What this is saying is that the y coordinate of the centroid of that rectangle is the average value of f of x sub I star and g of x sub I star. So that makes sense. If I want to find the what's in the middle here, we'll take the big one and the small one, add them up and divide by 2. So that gives me a y coordinate. So once I know the centroid, I can get an approximation for the moment. If I'm talking about the moment about the y-axis, then I would take the area and multiply that times the x coordinate of the centroid. And so then I turn that into an integral by letting n go to infinity. When I'm talking about the moment about the x-axis, again, what would I do? I would take the area. All right, so it's just going to be the f minus g times delta x. And then I'm going to multiply it times this y bar, which we just found out is the average of f and g. Now, when I look at this, I can do some algebra, right? I actually have, these are called conjugates, if you remember that. They're the same terms, but one, you have two terms, and in absolute value, they're the same, but the second one is positive in one case and negative in the other. And so we can write that as the difference of their squares. So that just comes from some basic algebra. So that gives us a little bit simpler formula to deal with when we get to the time to actually evaluate the integral. All right, so now we've got formulas for the moments about the x and the y-axis, and then if I just divide each one by a, if I divide the moment about the y-axis by a, I'll get the x-coordinate, and if I take the moment about the x-axis and divide it by the area, I'll get the y-coordinate of the center of mass. All right, so here's an example. And what we said previously about symmetry still holds, but there's no symmetry here. So there's still nothing that we can take advantage of in this particular problem. There is no line of symmetry. So I can just use the always thinking top minus bottom, right? So it's always going to be top minus bottom. So don't think about, well, which one is F and which one is G. Just think about which one is the top and which one is the bottom. So we can go ahead and take those formulas and go ahead and substitute it into the formula for the moments, calculate those moments. There's nothing very tricky here except for just being careful with all of the algebra. And again, applying it for the moment about the x-axis, I have to, again, take the difference of the square of the top minus the square of the bottom. Just be careful with all of any like terms that you may have. Collect those properly. And evaluate the integral. And it's always nice if you have a graph like we do here of the region to go ahead and plot where that centroid is and just use some intuition. Does that kind of look like there's, in the middle? Does it look like that would be balanced? And you could bear in mind that, okay, if it's balanced, it doesn't necessarily mean that you're going to have equal area on each side. Because remember, the further it is from a point, the bigger the moment would be. So it looks like this region above and to the right has more area, but it's closer to the point, whereas there might be less area down here, but we've got this portion down here, which is very far from that point, and that would counterbalance the extra area, which is close to that point on the other side. So you just want to kind of look at it and say, well, okay, that's kind of interesting. All right, so I'm going to stop here. I don't even know what time it is. Let me see. Oh, it's almost perfect timing. So why don't we take a 10-minute break here and we will come back. And I don't know if you've worked much with Zoom, but Zoom has this idea of what they call breakout sessions. And so we can go ahead and I'll create just some groups. We only have 12 people here. So before you go away, let me go ahead. I'm just going to quickly grab a screenshot of the participants here. And then we'll take a 10-minute break, at least a 10-minute break. All right, great. Thank you. So get back to my board.